Okay, y'all. So this is for Algebra 1. These are the first kind of videos of our Unit 5 notes that I'll be posting on our Google Classroom. So in case if you miss like a day, you can basically go back in and kind of watch the video, see the notes that we have kind of gone over for the day. So we're starting off with section 1, 5.1, the first section for solving systems of equations. And this first one is going to deal with solving systems by graphing. And we did a little bit of this. I'm recording this on a Sunday. We did a few of these notes on Friday, but we'll kind of go more in depth on them on the following Monday, which is tomorrow. So let's kind of go over and look at it. So a system of equations, it's basically two or more linear equations with the same variables. So basically what that means is, we've been dealing with, equations, let's say, like equation like 5x plus 1, okay? And, we've been solving, equations, solve for this equation or solve for that or whatever. Now, basically, what we do with systems of equations is we basically take not just one equation, but two, or maybe even more equations. Let's say, not even, let's say, I was about to write another 5 there. Let's say like a 3x, minus 3 or something like that. So basically, when we're dealing with systems of equations, we instead of having one equation, we're going to have two equations, maybe even more actually. And then from there, we're basically solving to find out, what x value or which y values, is going to satisfy not just this one equation, but both equations, all right? And normally, and as we say down here with the second bullet, solution of a system of equations is essentially an ordered pair. And again, ordered pair, it's two numbers, x comma y, an x value and a y value. It's an x value, and again, that would plug in here, and a y value, plug in here and plug in there. That satisfies both of the equations in our system. All right. And when we look at solving by graphing, we essentially want to look, in the first, step of solving is, by graphing, the kind of start with the non-mathematical way of doing it, but the way that we look at how to solve a system of equations is basically we have two lines because every one of these equations right here is going to give us a line. So like say, this is our first equation and then this is our second equation. And essentially where we want to look for, for our solution right here, the ordered pair that satisfies both, is where the two lines intersect at. That's essentially what we're looking for. We want to look for a point where they intersect at. And that point of intersection is going to be where our system, where our solution of our system is. Now, there's a couple different options. Now, there's a couple different options. They could obviously intersect at one point. They could also be the same line. You could literally have a system where you have, so let's say y is equal to, 3x and y is equal to 3x. That's a system of equations right there. That is the same line. If they intersect, now if I kind of go over my logic over here, we're looking at where the lines intersect at. But if they're the same line, they intersect at every single point. So that would mean that every single, point, every single, option would be my solution. So if it would be this one, it would be infinite solutions if they are the same line there. Now, over so you can have two lines that are in one plane that are the same line, or you could have two lines here that are parallel. Let's see. Let's say actually, when the lines are parallel, that means they basically have the same slope. So let's say y is equal to 5x plus 1, or y is equal to 5x minus 3. These two lines have the same slope, so they're going to be parallel. So now let's think about this, kind of with our logic over here. We're wanting to see where these two lines intersect at, and if they intersect at all the points, that means they're all the solutions, infinite solutions. But with parallel lines, they're never going to intersect. So if they never intersect, are they even going to have a solution? And the answer, of course, is no, there's not going to be a solution. So if they are parallel lines, you're going to have no solution. Okay? So again, that's kind of like a brief introduction of what we're wanting to look for with our system, graphing our systems of equations. We're just looking for where our lines intersect at, if they are even the same lines or even if they're parallel. Okay. So, and then we have like our types of linear systems. This is kind of, we like to classify our systems of equations. So we have a couple different ones. We have consistent independent, or what we would classify as CI. And these are basically the lines that essentially intersect at one point. All right. Consistent independent CI, they intersect at one point. They have different slopes. Again, different slopes. They intersect, and there's only one solution. All right. Consistent independent have one solution. All right. That is the solution where you get the one ordered pair, like the one x equals y pair right there. Okay. So then we have consistent dependent, or that we would classify as CD, that are the same slope, same y-intercept. Literally, they are the same lines. These are the infinite solution systems of equations. If we were to see a system of equation that graphs the same line that have infinite solutions, we would classify these as consistent dependent equations, or consistent dependent solutions, or no, systems, excuse me. Again, consistent dependent, the systems that have our infinite solutions that are essentially the same lines on top of each other there. And then the last ones, we have our inconsistent, or that we would just classify as I. They are systems that have the same slope but different intercepts. So because again, lines that are parallel have the same slopes, but they're just have different y-intercepts, obviously. So these lines are parallel, and these are the systems that have no solution. So again, inconsistent systems of equations have no solutions. Same slopes, but different intercepts. So we can automatically classify systems of equations by honestly not even just looking at the graphs, but even looking at the types of equations of lines they have, which we can do right here. So just kind of quickly going through some of these here, we have a couple graphs over here and a couple equations, and we just need to classify, what I'm just going to classify. It does say state the solution. I'm not going to do that. I'm just going to classify whether they are consistent independent, consistent dependent, or inconsistent. So going over here, number one, we have two lines here that are parallel. It looks like they are straight lines that don't look like that are not sloping down at all. These are two parallel lines that are not going to have a solution. There's no solution to this system. So this number one right here is going to be an inconsistent, or an I system of equation right there. Number two right here, all right, we see that there is a single point of intersection. There is one solution. Let's say it's at like -5, -6, or something like that. All right. But because it has this one point of intersection, it is going to be a consistent dependent, or a consistent independent system of equations. We're going to label it as CI, all right, because it only has one solution. Now, 5 is kind of tricky. You gotta have to think a little bit outside the box, quite literally, for this one, is because these are not parallel lines, because they're obviously slanted toward each other. But it doesn't look like there's a point of intersection on the graph here. But if we know these arrows right here, they tell us that they're going to keep going up. They're going to intersect at some point. We don't know where, but they will intersect at some point there. And again, because they have that single point of intersection there, it's going to be a consistent independent graph right there, a CI graph right there. And then last but not least, we have number 6 right here. These are two lines that are just right on top of each other. These have infinitely many solutions. Again, any system that looks like this is going to be a consistent dependent system, or just a CD system right there, all right? So we have our consistent independent systems right here, inconsistent systems right here, and our consistent dependent. Now we can determine that. We can even determine, this classification by just looking at the lines here. And the main thing is, number one, look at the slope. All right, look at your slope and look at your intercepts. If they have the same slope and the same intercept, they're going to be a consistent dependent system, because -3 y is equal to -3x minus 2, y equals -3x minus 2. That's literally the same line. It's going to look something like what we had in number 6 here. So this, we have the same slope, same y-intercept. This is going to be a consistent dependent system right here. Same for this one right here, number 4. Same slope, same y-intercept. All right, these are the same lines This is going to be a consistent dependent system of equations right here. Going down to number 7, hey, look at that. We have the same slope, but we have different y-intercepts. This system is going to look a lot like what number 1 is. Oh, excuse me. It's going to look a lot like what number 1 is. It has the same slope, but it has different intercepts. So it is going to be an inconsistent equation. Because again, same slope, but different y-intercepts, all right? And then last but not least, for number 8, we can tell that automatically these are different slopes. Different slopes, so we don't even worry about where the y-intercepts are. They could even be the same y-intercepts, but they have different slopes, so we know that this is going to be a consistent, independent equation system, because we know that these are going to be different slopes, so it's going to be kind of what number 5 or number 2 looks like. They're going to intersect at a single point there. Okay, so let's go ahead and graph a couple of lines. You know, we did, this is the part of the class that we did on Friday. So let's go ahead and graph a couple of these and kind of go from there. Let's look and see what we can do here. So, and again, we could, you know, look at our equation and see, hey, you know, this is going to be CI, CD, or I, or whatever, but let's just go ahead and graph it just to make sure. So I'm going to graph this first line in red, and then this last line, probably graph it in blue. Start with the blue line. So y is equal to negative 1/3 x plus 6 right here, okay? This is a slope-intercept form. We have done a lot of graphing in the past, so again, start with our y-intercept right here. This is our y-intercept. It's at positive 6, so we're going to graph a point right there at positive 6. My slope is negative 1/3, so I'm going to go down 1, and then to the right, 1, 2, 3. Because again, this is going to make a negative slope. And then for a better measure, let's do it the opposite way. I go up. I go a positive direction, but then if I go positive in the up, I have to go negative in the left or right. So I'm going to go left 1, 2, 3. And so my line's going to look something like that. It's not a perfect line. And then I'm going to graph y is equal to negative 1/3 x minus 4. Start with my negative 4. That is my y-intercept. Y-intercept, again, that's this axis that goes straight up and down. So I'm going to graph it, the negative 4 right here. And then I'm going to go, same as I did with the slope down here, I'm going to go down 1 and then to the right 3. I'm going to go up 1 and then to the left 3. And that's going to give me a line that looks something like this, okay? And again, this is, you know, not a perfect line, not a perfect drawing, but, you know, if we can see, these are going to be parallel lines because these have the same slope, but they have different y-intercepts, excuse me. So we are going to classify this as an inconsistent system of equations because our solution, these are never going to intersect. I'm not going to even have a solution, so it's going to be no solution. Okay? Moving on to this one right here. So let's go ahead and graph it. So again, I'm going to do the different colors. I got red. I'm going to start by graphing this first one in red. Negative 1/4 x minus 3. So again, start with this number here, the negative 3. On my y-axis, I'm going to go down to here. And I'm going to graph it. You know, I have 1/4. I'm going to go up 1 over 1, 2, 3, 4. Down 1 over 1, 2, 3, 4. That's good right there. Let's go ahead and graph the blue equation right here. 3/2 x plus 2. I start with the last number here. That is my y-intercept. I go up to 2 on my y-axis right here. And I use my slope, 3 over 2. I'm going to go up 3 over 2. I'm going to go down 3, 1, 2, 1, 2, 3, and then over 1, 2 to the left. And then I'm going to do it one more time. Down 1, 2, 3. Actually, wait. 1, 2, 3. Up should be right up here, excuse me. And go over, down 1, 2, 3, over right here. And if we look at that, we see that our lines are going to intersect at a single point. That point just so happens to be this point right here, which is negative 4, negative 4. I have one solution, so that tells me that my system is going to be a consistent independent solution of equations right there. Okay? And lastly, real quick, these are the same lines, same slope, Same intercept. These are going to be consistent, independent with infinite